Welcome to today's deep dive. So I want to start by asking you a question. Have you ever, written a sticky note to remind yourself how to do a task?
Oh, yeah. Absolutely. My monitor used to be covered in them.
Great, because, maybe it was a weird quirk of some new software you were learning or a highly specific way your boss wanted a weekly report formatted.
Right. You need that immediate reminder.
Exactly. You stick it right on the edge of your monitor. But then as you get better at the job over the next few months, your fundamental approach to the work changes.
Yeah. Your skills evolve.
Oh,
You get faster.
yeah. And suddenly that sticky note isn't just useless. It actually contradicts how you work now. Like if you followed it, you'd actually mess up the task.
Right. Because the instruction no longer matches your internal capability. You basically outgrow your own manual.
Exactly. And this is the exact wall that AI developers are hitting right now. Today's deep dive is into a massive leap forward in how autonomous AI agents learn from their mistakes.
And it's really fascinating stuff.
It really is. We are looking at some recent research out of Sun Yat-sen University on a framework called JRP. That's Joint Learning of Experiential Rules and Policies.
Yeah. JRP.
Right. And to set the stage, we are talking about complex LLM agents navigating multi-step environments. So like browsing a simulated web store to buy you shoes or navigating a digital house to clean it.
Which is super hard for an AI. Because these are environments where the agent isn't just answering a trivia question in a chat box.
Right. It's not just a search engine.
Exactly. It has to take an action, observe how the environment changes, and then, plan the next move based on that. And historically, the AI engineering world has tried to solve this learning problem using two parallel but entirely isolated approaches.
Okay, right. So let's set a quick baseline for everyone on that. Usually, developers either rely on prompt engineering, where the agent's past experience is saved as text rules and fed back into its prompt, or they use reinforcement learning fine-tuning.
Which is entirely different.
Right. That's where the environmental feedback is used to update the actual neural weights of the model itself.
Yeah, so you're looking at explicit knowledge versus implicit behavior.
Which goes back to the analogy, the sticky note on the monitor versus building actual muscle memory.
Exactly.
But the glaring problem I always see with this is that they are treated as completely separate parallel universes. Like if I update my muscle memory but leave the sticky note the same, I end up with that cognitive dissonance we were just talking about.
Yeah, and in AI agents, it creates a severe bottleneck. The two methods have complementary limitations when they are isolated from each other.
How so?
Well, explicit text rules are fantastic for fixing local recurring errors. Like if an agent keeps forgetting to turn on a light before looking under a bed, a text rule fixes that instantly.
Oh, I see. It just reads, turn on the light first.
Right, but rules don't execute themselves.
Yeah.
If your model's internal policy, its neural weights, is evolving through fine-tuning, those static text rules fall completely out of sync with how the agent actually operates now.
They become stale.
Yeah, stale and actively misleading to the AI.
But on the flip side, you can't just rely on weight updates, right? I mean, in these complex multi-step tasks, the rewards are what they call sparse.
Very sparse.
Like if it takes 30 steps to buy a pair of shoes online and the agent fails at step 29, it just gets a 0 for the whole run.
Exactly. Which means updating the global neural weights might completely miss the specific local mistake the agent made at, say, step 14.
Oh, wow.
Yeah, the feedback is just too diffuse to teach it that one granular lesson.
So keeping them separate causes the agent to literally fall out of sync with its own instructions. The explicit notes get outdated, and the implicit muscle memory misses the fine details.
Right. It's a real dilemma.
Which brings us to the JERP framework. Because the Sun Yat-sen researchers found a way to bind them together. They're updating both the text rules and the neural parameters simultaneously from the exact same interaction trajectories.
And to really understand how they achieve this, we need to look at how the agent preps for a task. Because before it takes a single step, the agent accesses what they call a long-term experiential rule pool.
Okay, so like a database.
Yeah, it's a massive database of text rules it has acquired over time from past runs.
Wait, it can't possibly load all of those into its context window, though.
Right.
Like, it would be paralyzed by information overload if it had to read 10,000 rules.
Oh, it doesn't. Not at all. Every rule in this pool has a dynamic utility score attached to it. So the system retrieves only a highly targeted subset, the top scoring rules that are most relevant to the current task.
Ah, okay.
This becomes the working rule set, which is then injected into the prompt.
So it's looking at the monitor, but it's only picking the 3 sticky notes that actually apply to the specific spreadsheet it currently has open.
That's a perfect way to picture it, yeah.
Yeah.
From there, the agent attempts the task, and it's usually exploring multiple different paths simultaneously.
Right.
This generates a batch of complete attempts at solving the problem, which the researchers call a trajectory group. And this group is the raw material used for the first major mechanism, updating the neural parameters.
Okay, and they use GRPO for this, right? Group Relative Policy Optimization.
Yes, exactly.
I'm really glad we are looking at this because a lot of older reinforcement learning methods rely on a completely separate, massive value model just to estimate how good an action was. And those value models are notoriously expensive to run.
Oh, they essentially double your compute costs. It's a huge burden. But GRPO sidesteps that entirely.
How does it do that?
Well, instead of a separate model calculating an absolute value for every single state, GRPO looks at the entire group of trajectories the agent just generated for a specific prompt. It calculates the mean and the standard deviation of the rewards for that specific group.
So it's grading on a curve. The algorithm isn't demanding absolute perfection in a vacuum. It's looking at all the attempts the AI just made and saying, hey, compared to your own group average, this specific sequence of actions was an advantage, and this other one was a disadvantage.
Right. By standardizing the rewards within the sampled group, the system constructs a relative advantage. It then pairs this with low rank adaptation to efficiently update the neural weights.
So it nudges the parameters to favor the actions that performed above the curve.
You got it.
Wait, I actually have a problem with the curve grading concept.
Oh, what's that?
Well, if an agent is totally untrained, and the whole group of trajectories is just terrible, I'm picturing the agent just walking into walls for 30 steps straight. Grading on a curve means you're still rewarding the least terrible option. Doesn't that risk reinforcing bad behavior?
It sounds like it would, yeah. But in early training, that is actually a mathematical necessity.
Really?
Because if you only reward absolute success, an untrained agent will literally never learn anything. It will never accidentally stumble upon a flawless 30-step success sequence to get a positive reward.
Oh, I see. It would just be all zeros all the time.
Right. Grading on a curve gives the model a gradient to follow, even in a sea of complete failures. It learns that, hey, walking into a wall once is slightly better than walking into it twice.
Okay, yeah, that makes total sense. You need, breadcrumbs to follow out of the dark.
Exactly.
So the neural weights are successfully updated using this relative advantage. But that's just the math part, right? We still have to update the text rules, the actual English sentences on the sticky notes, and you can't really use gradients in calculus to adjust a preposition in a sentence.
No, you definitely can't. And this is where the researchers introduce something called contrastive reflection.
Contrastive reflection.
Yeah. The system has to update its text rules using the exact same trajectories it just used for the parameter updates.
But how does a mathematical framework reliably edit a natural language text rule without just, garbling the sentence into complete nonsense? Language is way too messy for numerical optimization.
They don't use numerical optimization for the text. They deploy a secondary LLM with its parameters completely frozen.
Frozen?
Yes. And they prompt this frozen model to act as a highly structured, strict copy editor for the agent's rulebook.
A frozen LLM copy editor. Okay, so it's literally reading the successes and failures and rewriting the text rules based on what it observed.
Exactly. It compares the current batch of trajectories against a saved set of referenced successful trajectories. So it's looking for the contrast between them.
Right.
But to prevent the copy editor from hallucinating or just creating chaos, it is restricted to a very rigid edit syntax. It could only execute 5 primitive operations.
And what are those?
ADD, edit, uput, downvote, and merge.
Okay, ADD and edit are pretty self-explanatory, creating a new rule or tweaking an old one. But let me push back on upvote and downvote for a second.
Sure.
If an agent uses, say, 10 different rules in a single 30-step trajectory and it fails at the very end, how does the copy editor know which rule to downvote? Doesn't it risk punishing a perfectly good rule just because a completely different step failed later on? The credit assignment there seems impossible.
And that is exactly the beauty of the contrastive approach. The frozen LLM isn't just looking at the final score. It aligns the failed trajectory side by side with the reference successful trajectory step by step.
Oh.
Yeah, it looks for the exact divergence point, the specific state where the failed run deviated from the successful run.
Oh, wow. So it pinpoints the exact moment things went off the rails.
Exactly. It isolates that specific state, looks at which text rule was applied at that exact moment, and downvotes only that specific rule.
That's incredibly precise.
It is. And if a rule's utility score drops below a predefined threshold, it is deleted entirely. The pool is pruned of outdated information.
Okay, that solves the credit assignment problem perfectly.
Yeah.
But honestly, the operation I find most fascinating in this whole paper is merge.
Oh, merge is critical for long-term viability. Think about what happens as an AI agent interacts thousands of times in an environment.
It probably generates tons of rules.
Right. It might independently generate 50 different rules about how to turn on a lamp or how to open a door.
And if you keep all of them, the rule pool hits its capacity limit, and the context window gets bloated with repetitive overlapping noise. Like, you don't want 50 notes on your monitor saying the exact same thing in slightly different words.
Exactly. The merge operation takes semantically similar and functionally overlapping rules and compresses them into a single, comprehensive rule. It keeps the knowledge base efficient.
But what happens to the scores of those old rules?
Mechanically, the new merged rule arithmetically inherits the maximum utility score of the original rules it replaced.
Ah, so it doesn't lose its priority status in the retrieval phase. Okay, so we now have the complete JRP paradigm. We are upgrading our implicit neural parameters via group relative curve grading, while simultaneously our frozen LLM copy editor is pinpointing divergence points to ADD, ADIT, and merge our explicit text rules.
Right.
The two systems are finally learning from the exact same mistakes in perfect sync.
The architecture is elegant, really.
Yeah.
But its true value is only proven in how it handles real-world complexity.
Right. Theory versus practice.
Exactly. So the researchers deployed this framework in two demanding arenas, AlfWorld and WebShop.
I actually know AlfWorld pretty well. It's a text-based household environment that requires really complex multi-step manipulation. You have to navigate rooms, find hidden objects, use tools, and satisfy very specific conditions.
Yeah, it's not simple at all.
Like a prompt might be, find a dirty bowl, take it to the sink, clean it, take it to the microwave, heat it, and then place it on the dining table.
Right, and WebShop is equally complex, but in a totally different domain. It's an interactive online shopping simulator. So given a user prompt like, I want a blue men's running shoe under $50, the agent has to search, browse, compare options across different pages, and execute the actual purchase.
Wow. So no hand-holding at all. The agent just has to explore and figure it out.
Exactly.
And when we look at the baseline results, the vanilla LLMs like agents with no memory architecture, just raw intelligence being prompted to solve the task, they failed spectacularly, right?
Oh, absolutely. On AlfWorld, the vanilla LLM had a success rate of just 4.1%.
4.1%. That's abysmal.
And on WebShop, it was 5.2%.
That proves something really important for anyone following AI development. Raw reasoning power is just not enough for true agency. An AI can have, like, all the world's knowledge encoded in its base weights, but if it doesn't have a structured architecture for learning from its immediate interactive experience, it is functionally useless 95% of the time.
It absolutely requires a system to process experience. Now, if we look at the previous state of the art, which was the GRPO method that only updates parameters without the text rules, it did much better.
Okay, what were the numbers there?
It achieved a 57.8% success rate on AlfWorld and 56.2% on WebShop.
I mean, that's solid.
It is, but JRP blew past it. JRP achieved a 61.5% success rate on AlfWorld and a 64.1% success rate on WebShop.
Wow. But why? Like, where was JRP pulling ahead?
Well, the aggregate numbers are impressive, but the breakdown of the specific AlfWorld tasks reveals why JRP works so well.
Okay.
AlfWorld categorizes tasks by complexity. In simpler tasks, like just pick an object or look at an object, the parameter-only GRPO method was highly competitive. It didn't necessarily need the text rules.
Right, because if you're doing something simple, implicit instinct is enough. You can kind of just wing it.
Exactly. But the performance gap widened massively in highly constrained tasks.
Like what?
Tasks labeled clean, heat, cool, and pick two, which requires picking two specific objects and placing them together. In these categories, JRP vastly outperformed everything else.
And that makes total sense when you think about the mechanics. If you have to pick up an apple, navigate to the fridge to cool it, and then navigate to a specific counter to place it, you need a highly specific recipe.
Right?
Implicit parameters alone just aren't enough to track the strict dependencies of those intermediate steps. You need those explicit rules retrieved into your prompt to keep you on the rails so you don't forget the constraints mid-task.
Yeah, the rules preserve the effective operation patterns for those long sequences. The parameter updates provide the general policy improvement like the instinct to navigate better, but the rule pool keeps the task-specific, step-by-step corrections available right there in the prompt.
Okay, but let me play devil's advocate for a second. How do we know for sure that it's the synchronization of these two things doing the heavy lifting? Could it just be that having a rule pool is generally helpful, even if it's static?
That's a great question, and the researchers proved synchronization is the key through a really revealing ablation study.
Oh, I love ablation studies. What did they do?
They ran a test where they trained a JRP agent, but partway through, they completely froze the rule pool. They essentially disabled the contrastive reflection copy editor.
So no more ADD, edit, or merge.
Right. The text rules were locked in place, but the neural parameters were allowed to keep updating via GRPO.
And what happened?
The performance hit a brick wall. It plateaued almost immediately.
Wait, really? Why? If the neural weights are still getting smarter, shouldn't the agent keep improving at least a little bit?
You'd think so, but because the environment is dynamic and as the agent's internal policy continues to evolve, the later trajectories expose entirely different kinds of errors and new useful behaviors that the agent didn't encounter in the early stages.
Right.
But because the rule pool was frozen, it couldn't absorb any of those new observations.
Ah, so the agent's implicit behavior drifted away from its explicit knowledge.
Exactly. It creates severe cognitive dissonance in the system. The rules in the pool were describing the capabilities and common mistakes of the agent from like 10,000 steps ago.
Oh, wow.
So when those stale rules were retrieved and injected into the prompt, they actively conflicted with the agent's newly optimized neural pathways. The agent was being forced to read its own outdated beginner notes while trying to execute advanced techniques.
It's exactly the sticky note problem we started with. Like, if you force an expert to strictly follow a beginner's manual, they actually perform worse than if they had no manual at all.
Yep.
This ablation study is honestly the smoking gun of the whole paper. It proves that continual, simultaneous rule updating is the absolute secret sauce to the system's success.
Without the synchronization, the dual-track system basically collapses under its own contradictions.
So, stepping back from the math and the specific AI benchmarks for a minute, the ultimate takeaway here is profound. True effective agency, whether artificial or human, isn't just about throwing computing power at neural weights, and it isn't just about engineering massive static instruction manuals.
Right.
It's about the synchronized marriage of explicit knowledge and implicit behavior. Both systems have to learn from the exact same mistakes at the exact same time.
Bridging the gap between what a system knows it should do and what it instinctively does under pressure.
Exactly. And if you're wondering how this applies to your own life, think about how you approach mastering a complex new skill, whether it's in your career or a hobby. Are you relying too much on stale, outdated notes you wrote months ago?
Or are you just flying by the seat of your pants, hoping your implicit instinct will eventually figure it out through trial and error?
Right. Real mastery requires you to constantly actively revise your internal rules while you practice. You have to be your own contrastive reflection copy editor.
You have to edit your own sticky notes as your capabilities change.
Which leaves me with one final, slightly mind-bending thought for you to mull over. We just walked through how AI agents are now capable of automatically merging, editing, and pruning their own natural language rules, perfectly optimizing them for their own rapidly evolving neural parameters. If they can do this for themselves, how long until these agents start writing operational manuals for each other?
Oh, wow. That's a wild thought.
Right. And if an advanced agent writes a set of explicit text rules perfectly tailored to the neural pathways of another AI, will those manuals eventually become entirely incomprehensible to us human engineers? Will we even be able to read the sticky notes of the future, or will they be written in a dialect of logic that only makes sense to a machine? Definitely something to think about. Thanks for joining us on this deep dive.